All right, we're going to start geometry today, and we're going to begin with, basically we're going to begin with basic definitions and terminology. And so also we're going to be going through your book, section 12.1. So I'm going to begin with kind of some abstract concepts that are actually very foundational. We are going to cover both plane geometry and solid geometry. Plane geometry, of course, exists in 2 dimensions. Solid geometry involves solid figures and 3-dimensional objects. So we'll begin with just basic foundational definitions. There are 3 kind of abstract geometry ideas that are a little bit hard to define, but they are very foundational because we're going to be defining our other definitions from them. The first is point. How can you define point? What is a point? Well, it's defined as a particular location in space. So a point can be in a plane or it can be in space. It is both a plane figure and a solid figure. So a point represents a particular location in space. It has no length or width. 2 ideas with point. Point is represented with a period. Okay, so we use a period or a dot, whatever you want to call it, to represent our point, and it is defined as a particular location in space. Secondly, the point is symbolized with a capital letter. So when we have a point, we use a period to represent it, and then when we name it, we use a capital letter. Keep in mind in mathematics that there's differences between lowercase and uppercase. So you can't just do what you want and sometimes do uppercase because you like to write in caps, sometimes do lowercase because you like to write in cursive or whatever. Basically what we do in mathematics is we use uppercase for vertices, we use uppercase in formulas for particular concepts. Lowercase is used pretty much for sides. Lowercase is used for lengths. Lowercase can be used to name particular things, but there's a difference between uppercase and lowercase. So don't interchange them or allow your students to. Okay, so we're going to use a capital letter, a print capital letter, or manuscript, I guess you call it. Whereas with the lowercase, we want to use cursive. So in geometry, the case and style of writing is particular. Uppercase, we use manuscript, and it's for vertices and points and geometry symbols, whereas lowercase represents sides and distances and so forth. And we want to use cursive for lowercase, and that includes algebra as well. All right, so then a point is a particular location in space. It has no length or width. It is represented with a period, and it is symbolized with a capital letter. The next figure, our first is point, then we have line, and then we'll have plane. A line is also kind of difficult to define, but it is a very foundational figure that we're going to use to define others. So a line is an infinite number of points extending in opposite directions. It's an infinite number of points extending in opposite directions. Okay, some ideas here. First of all, it is represented by a straight line ending with arrows. Lines, we use, obviously we're going to use a line, but make sure that when you denote a line that you have arrows, indicating that the line extends indefinitely, indicating that the line is infinite. So a line is represented with arrows on the ends of the line. Another idea, it's symbolized either as uppercase with 2 points or as a lowercase. So if we have a line we are going to represent it with arrows. We can represent this as line L, lowercase, or we can represent it, let's say we have the point C and D on it. We also represent it using any 2 points on it. That is line CD. All right, so we can represent it with either a lowercase letter, call that line L, or we can represent it with 2 points that are on it with the line symbol above it. You might see this. You might see CD by itself without a designation of segment or line or ray or anything on it. And then when you see it without the symbol, it's referring to distance between. Okay? So this is line CD. This would be the distance between C and D. So just a little bit of difference in notation. So a line is an infinite number of points extending in opposite directions. It's represented obviously with a line, but make sure you have the arrows indicating that it is indefinite. Can be symbolized with a lowercase letter or with 2 points on it. Another thing about lines is that lines are determined by 2 points. You probably remember from geometry a theorem that stated that 2 points determine a line. So if I'm going to designate a line, I need to name it by 2 points. If I'm going to confirm a line, I actually need 3 points, because any line can be drawn between any 2 points. If I want a particular line, obviously I have to name it by 2 of its points, but to confirm that it is accurate, it's always a good idea to find a third collinear point. Third definition is a plane. A plane. A plane is a 2-dimensional surface having infinite length and infinite width. It's a 2-dimensional surface. The key word is surface. It's a 2-dimensional surface having infinite length and infinite width. So we have a point. A point represents a particular location in space. It has no length or width. A line is an infinite number of points extending in opposite directions. I suppose we could say that a line is 1-dimensional because it does have length. Now the third foundational definition is plane. A plane is a 2-dimensional surface having both length and width. Okay? And so the 2-dimensional surface is both infinite in length and infinite in width. A plane is usually represented by a parallelogram. And sometimes the parallelogram will just be a parallelogram. Other times it will have arrows indicating that it extends infinitely, both in length and width. 2-dimensional surface having infinite length and infinite width. It's symbolized with a parallelogram. With a plane, 3 non-collinear points determine a particular plane. Remember, 2 points determine a line. 3 non-collinear points will determine a plane. All right, so our foundational definitions are point, line, and plane. Then what we can do is we can take line, and from line we can define various other plane figures, and even figures that are not limited to a particular plane. So lines, let's take and talk about lines for a while. We're going to talk about special lines, we're going to talk about types of lines, and then properties of lines. So first of all, other figures that are defined with respect to line. There are 2 other figures we could take on the board. We have line CD, but also on the board we have segment CD, and we have ray CD. Okay, so first of all, segment. Segment is a plane figure that we define with respect to line. So what is the definition? A segment is part of a line having two endpoints. Part of a line having two endpoints. So segment CD is only the part of the line between the two endpoints C and D. That is a segment. All right, then the next figure that we would define with respect to line is a ray. A ray is part of a line, just like a segment. A segment is part of a line, and a ray is part of a line having one endpoint and extending indefinitely in the other direction. So a ray is part of a line having one endpoint and extending indefinitely in only one direction, or in the opposite direction. Okay? So we can define segment and ray based on the line itself. So we have line CD, segment CD, and ray CD. We also have ray DC, because we can have this ray starting at C as its endpoint and extending through D, or we can have the ray whose endpoint is D extending through the other point C. So we have three different figures on that particular diagram. All right, now we're going to talk about types of lines. There are three basic types of lines: intersecting lines, parallel lines, and skew lines. Types of lines: intersecting lines, parallel lines, coplanar line, or skew lines. We'll begin with intersecting lines. Intersecting lines are two coplanar lines, meaning they're in the same plane, that share a common point. In other words, they intersect. So intersecting lines are two coplanar, could be more than two, but basically we have two or more coplanar lines that share a common point. And that point, of course, is the point of intersection. So intersecting lines, they have to be in the same plane. Then we have a special type of intersecting lines. They're called perpendicular lines. Perpendicular lines are intersecting lines that form right angles. Intersecting lines, basically any two or more coplanar lines that share a common point, but in particular we can have perpendicular lines. Perpendicular lines are intersecting lines that form right angles. This means that they intersect at exactly 90 degrees. The angles formed are 90 degrees. They're right angles. Symbol for perpendicular. If we were to take another line and bring it here through intersecting, we'll call this line AB, and we'll call the point of intersection, we'll call it E. So if AB intersects CD at exactly 90 degrees, it is perpendicular. On diagrams, perpendicular is denoted by a little square in the corner. If we are writing it out symbolically, we would say line AB is perpendicular to line CD. All of this should be very familiar to you, terminology and symbols and so forth. So intersecting lines are coplanar. There are two or more coplanar lines that share a common point. In other words, they intersect And in particular, we can have perpendicular lines. These are intersecting lines that form right angles. They are denoted by a perpendicular symbol or a little square in the corner. So intersecting lines. Now, parallel lines. Parallel lines are two or more coplanar lines that never intersect. They have no points in common. Parallel lines, they also have to be coplanar. So these are two or more lines that never intersect. They share no common points. A couple ideas with parallel lines. Parallel lines have equal slopes, meaning that as the slope, of course, is a ratio of the vertical change to the horizontal change. In other words, how steep the line is. It's the ratio comparing how quickly it's rising as it moves across the page. That slope, parallel lines have equal slopes. That's why they will not intersect. Parallel lines are denoted by the symbol. If we were to draw another set of lines over here, I always try to draw things at kind of odd angles. We don't want to give the students the impression that everything has to be straight up and down. Also try not to draw right triangles when I don't want a right triangle. I also want to not always draw the triangle in the same orientation. Sometimes you kind of flip it on its side because especially 5th graders, 6th graders, elementary students get confused when you start rotating things. So that's why I'm kind of going at an off angle here. Those would be two parallel lines. I don't want to put them vertical. I don't really want to put them horizontal because that might imply that they have to be, especially horizontal. They don't have to be horizontal. They have to have equal slopes and they cannot intersect. So let's say I have two parallel lines. We'll call this DE and FG. Or sometimes you'll see line L. Very rarely will you see line M. Does anybody know why we stay away from the letter M? Slope. We use it for slope, so we kind of stay away from it. They use line L a lot, maybe line T. Well, that might be the transversal. Let's do line N. That's a safe letter. So if I have parallel lines, I can say line L is parallel line N, or I can say line DE is parallel line FG. So it's denoted with those two thin bars very close together, parallel lines. So parallel lines and intersecting lines, which include perpendicular, they have to be coplanar. The third type of line is skew, S-K-E-W. Skew lines are two or more lines in different planes. If the lines are in different planes, they can't be intersecting, they can't be parallel, it just doesn't apply if they're in different planes. They might have a line going up here and a line going through here. They're not intersecting, they're in different planes, they're called skew lines. So we can have intersecting lines, perpendicular lines, parallel lines, skew lines. All right, properties of slopes. Property of slopes, that's my first property. Property of lines. First property is that a line is one-dimensional. It has only length. We can denote length with either this, the distance between, or we will denote length with the lowercase letter L. Make sure you write it in cursive so it doesn't look like the number 1. So properties of lines, first of all, they are one-dimensional only. They only have length. Secondly, lines are associated with distance. Length and distance are pretty much interchangeable in geometry. We would define length as the distance between 2 points. So when we're dealing with lines, we are dealing with one dimension, length, and we're dealing with distance. A third idea is slope. Slope is an important characteristic of a line. It is denoted with the lowercase letter m always, and it is a ratio. The ratio of the vertical change compared to the horizontal change. Sometimes it's referred to as rise over run, or little m can be the change in y over the change in x, but this is for when we are doing the xy coordinate plane. If you remember from high school, the xy coordinate plane is also two-dimensional. It has a horizontal reference line called the x-axis and a vertical reference line called the y-axis. So vertical on the xy coordinate plane is associated with the y-coordinate, horizontal with the x-coordinate. So it is a ratio of the vertical change to the horizontal change, the rise over the run. And practically speaking, it's going to tell how steep the line is. With slope, if we have a positive number, the slope is rising or going uphill as you read across the page left to right. Negative slope is downhill. Slope of 0 denotes a horizontal line. Okay, so slope is an important characteristic. M is 0 if we have a completely horizontal line. If my diagonal line is going uphill, it's positive. If it's going downhill, it's negative. Who knows about vertical? If a line is exactly perpendicular to the horizontal, we call it vertical. What do you know about the slope of a vertical line? It is undefined. There are no numbers that fit. That's the little symbol for null set. It's undefined because if it's vertical, there is no horizontal change, and that would give us a 0 in the denominator. So slope is an important property or characteristic of lines, denoted little letter m. It is a ratio comparing the vertical change to the horizontal change, commonly called rise over run, tells how steep the line is, and diagonal slopes going uphill are positive, diagonal lines going downhill have a negative slope, horizontal has a slope of 0, vertical is undefined. There is no slope if the line is vertical. So properties of lines: one-dimensional, involves distance, has a slope. Okay, so we have the properties of our lines. Before we leave the idea of lines, and this is kind of true in anything that you do with geometry, and you need to teach this to your elementary students and your junior high students so they don't do this when they're in high school. And that is the idea is never assume, so this is the last point under properties, never assume a property that you are not given. Never assume a property that you're not given. What do I mean by that? Just because it looks parallel, you don't assume it's parallel unless you're told, or it's part of what we call in geometry the given. We have to be given the fact that the lines are parallel in the directions or with symbols. We have to be given that the lines are perpendicular, either with symbols or in the diagram. Don't assume, especially the idea of parallel and perpendicular. Don't assume correspondence. Don't assume anything. Don't assume that something's a square. Even if it looks like a square, you have to be told that it's a square. Okay? How can I tell you that it's a square? I can say square ABCD, or I can do this. Remember how things are denoted? If I want to tell you that it's a square, I have to tell you that it's perpendicular. What else do I need to tell you? That all the sides are equal. Remember, if you put one slash through, this tells that the consecutive sides are all equal. It's probably overkill to put a little box everywhere. You could. But if all the sides are equal, then all the angles have to be equal, so it's kind of an overkill. But the principle applies whether we're talking about lines or we're talking about plane figures. Don't assume a property unless you are given that it's parallel or perpendicular, either in words, in the directions, or in symbols, or on the diagram. You must be given that it's parallel, perpendicular. You must be told that it's a square or told that it's a rectangle, okay? Because those are special quadrilaterals. You don't have to be told that it's a triangle, because a triangle is any three-sided polygon, right? But you would have to be told that it's a right triangle, okay? You don't go by what it looks like. All right, so those are lines, the types of lines, the two special lines, properties of lines. The next thing that I want to do is talk about plane figures. These are figures that usually exist in a plane because they are two-dimensional. They are figures that usually exist in a plane because they are two-dimensional. These are figures that it's easy for me to write on the blackboard because the blackboard is two-dimensional. When we get to solid geometry, that can be challenging to draw a three-dimensional figure on a two-dimensional blackboard. So plane figures are figures that usually exist in a plane because they are two-dimensional. We're going to talk about angles, and then polygons, and then circles. So we have three plane figures: angles, polygons, and circles. An angle, first one, angle. An angle is two rays that share a common endpoint called the vertex. Okay, so we have two rays that share a common endpoint called the vertex. Angles are denoted with drawing the angle. I have to get rid of some of our lines here. Angles. Two rays that share a common endpoint called the vertex. I'm just going to draw an acute angle for starters. I'm not going to draw something that even looks right angle. And there are different ways to represent this with symbols. We will use angle. We can call this angle B. Of course, the key point of an angle is its vertex. B is the common endpoint. B is the vertex. We always name an angle with respect to its vertex. This is angle B. I can also name it with in fact, if there's other angles involved, I would name it with all three letters. The B must be in the middle. Typically, we go in alphabetical order. There's no difference between these two. We don't care if we're going this way or this way. All right, we can also name angles with numbers inside, especially when we have a figure with multiple sides. We're going to denote the angles with angle 1, angle 2, angle 3, because it gets cumbersome to be doing A, B, C. Maybe I have another angle coming off here, angle DEA, or angle DBC. It gets confusing. So often, especially if we have more than one angle in a more complex figure, we can denote them with a number inside. Also, some textbooks use this. And that has the idea of the measure of the angle. Okay? So you might see these referring to the diagram, to the angle itself. We'll put a little M in front of it, maybe a little slash through it that denotes how big is this angle? What is the measure of this angle? Of course, in degrees. We won't use radians till high school. So our first plane figure is the angle. An angle is two rays that share a common endpoint called the vertex. And then there's the different ways that angles can be symbolized and referred to and named. Then a second idea with angles is that angles can be classified in different ways. Angles can be classified basically in three different ways. We can classify angles according to their degrees, according to their location, or according to the relationship to other angles. Let's begin with the first way. We can classify angles is according to their measurement, the number of degrees. You should recognize these: acute, right, obtuse, straight, and reflex. Later on in mathematics, we will define our angles with respect to the unit circle. If you took pre-cal or upper level math, you did a lot of things with the unit circles. So the unit circle, of course, is on the XY coordinate plane, and it has a radius of 1. If you remember, if it's in quadrant 1, of course, this is always 90 degrees. Acute angles would be anything, if we have the terminal ray here, or the initial ray rather, the initial ray here, and then the terminal ray can be anywhere in quadrant 1. An acute angle is any angle that is less than 90 degrees. And when we're dealing with the unit circle, or when we're dealing with the XY coordinate plane, this is called the initial ray, because we are rotating it, and the terminal ray. Now, you're not going to give all these details out to your elementary student, but this is background that you need to make sure that you understand geometry much better than they do, obviously, and at a higher level so that you don't mislead them. So we have acute angles. Acute angle is any angle that is less than 90 degrees. A right angle is 90 degrees. All right, and obviously it's associated with perpendicular lines. There's a theorem you learned in geometry: perpendicular lines form right angles. All right, so a right angle would be what's called a quadrantal angle. It would be right here, exactly 90 degrees. Then we have obtuse. Obtuse angles are in quadrant 2. Here's quadrant 1, quadrant 2, quadrant 3, quadrant 4. Remember your XY coordinate plane? Obtuse is in quadrant 2. That means we'd have our initial ray still on the positive x-axis, and then our terminal ray would be rotated somewhere in quadrant 2. So an obtuse angle is greater than 90 but less than 180. Then we have a straight angle. A straight angle would be actually the x-axis. Initial ray and terminal ray on the x-axis. A straight angle is equal to 180 degrees. It is a line. Then we have reflex. Reflex are angles that are in here. They're greater than 180. And of course, on the unit circle, we would probably not deal with anything more than 180. We would go with negative angles and all kinds of confusing things that elementary students don't need to know. So we can classify angles according to their measurement, the number of degrees. Acute, right, obtuse, straight, reflex. Okay? And this is how we classify angles. I had trouble this year particular, other years as well, when the directions tell students to classify, they're fine. But when students are told to name, they want to do acute, right, obtuse, straight, when the book wants them to name the angles using the symbols and so forth. So you have to be very specific in your terminology, and what you want to do with your terminology, your instructions, what I mean, you want to be very careful with your instructions, and you also want to make sure your instructions line up with the textbook, so that when they read the directions, they understand what the textbook means. Even if you, like me, would probably like to say it differently. All right, so angles can be classified by their measurement, the number of degrees that they contain. Angles are also classified by their location. Location. The first type of angles, pairs that we see, are vertical angles. Vertical angles are the opposite angles formed when lines intersect. Vertical angles are the opposite angles that form when lines intersect. They're called vertical angles. I'm going to try to draw a better line than that. And I'm also not going to draw right angles. I'm going to have them intersecting at an odd angle. I don't want to do things straight up and down and so forth. Angle 1, 2, 3, and 4 are formed when those two lines intersect. Vertical angles are opposite angles that form when lines intersect. So you can see here we have angle 1 and angle 3 are vertical, angle 2 and angle 4 are vertical. And of course you learned in geometry that vertical angles are what? Equal. Okay, so we might as well introduce that while we're at it. So vertical angles are the opposite angles formed by intersecting lines, and there will be two pairs of equal angles. They have to be opposite, and so I want to draw my angles so that they look different in size as well, okay? So that we don't erroneously get the impression that these two are equal. Okay, so we can name our angles by location. If they are located at intersecting lines, they're called vertical angles. Then we also have another way we can name angles or classify angles is by adjacent angles. When we have two angles that share both a vertex and a ray. Adjacent angles share both a vertex and a ray. So we actually have three angles here. Let's go ahead and give them some points. A, B, C, and D. We have angle ABC, angle CBD, and then angle ABD. But the two angles in the middle are called adjacent angles. Adjacent angles are two angles that share both a vertex and a common ray. We can also name angles by location within other figures. Okay. In particular, we will deal with angles on and in circles. We have a circle. If we have an angle at the center of the circle, it's called a central angle. Okay. We can also have an angle on the circle. Something like this. We have the central angle, an angle whose vertex is the center of a circle, and its rays have to pass through the circle. Then we have an inscribed angle. That's an angle whose vertex is on the circle. whose rays pass through it. The rays have to pass through the circle, or at least end at the circle, either way. So we can name our angles by location, vertical angles, adjacent angles, and then angles that are associated with other figures, central angle, inscribed angle, and so forth. Yes?
What is the definition for central?
It's an angle whose vertex is the center of a circle, whose rays pass through the circle. Inscribed angle is similar, but its vertex is on the circle, and its rays pass through the circle. A third way we can classify angles is through the relationships to others. The first two deal with the measurement, complementary and supplementary. Okay, so we can name angles according to their relationship to other angles. First of all, in the measurement, you know complementary and supplementary. Complementary are two angles whose measures sum to 90 degrees. Supplementary are two angles whose measures sum to 180 degrees. So we can classify angles by relationship to other angles. First relationship is through number of degrees, through their measures, complementary and supplementary. Complementary is sum of 90, supplementary sum of 180. All right, then we can also name our angles or classify our angles by their equality to other angles. Two ideas here. We have congruent and corresponding. Okay, congruent angles are simply angles with equal measures. This is the symbol for congruent. Congruent itself has the idea that it is the same size and the same shape. Well, angle size, of course, determines shape, so congruent applies to angles if they are equal. Corresponding angles are angles on different figures in the same location that are equal. Angles on different figures, but in the same location on that figure, and of course they're equal if the figures are congruent or similar. Okay, and many of these relationships will come into play with a little figure that shows up a lot in elementary geometry and in junior high geometry, and that is two parallel lines cut by a transversal. This time I will make them horizontal so I don't cause any confusion. I'll be told that line L is parallel to line, we'll call it line K, and that T is a transversal. There's going to be 8 angles formed here. 1, 2, 3, 4, 5, 6, 7, 8. And we have lots of relationships that we can work with here. But even if we go back to our vertical angle, we said earlier that angle 1 equals angle 3 because vertical angles are equal, and angle 2 equals angle 4, same reason. They're vertical angles, they're equal. What other relationships are even on this line? Well, let me rephrase that. What other relationship is on this line? Well, let me help you. If angle 1 is 110 degrees, just let's say, what is angle 2? Morgan?
70 degrees.
Why?
Because it's third complementary.
Not complementary.
Supplementary.
Supplementary. All right. So we can always find the measure of other angles based on their location and based on what we know about the figure. If I have two adjacent angles on a right angle, then they would be complementary. So angle 1 and angle 2 are complementary on this figure because they're in a right angle. Angle 1 and 2 on the vertical angle figure are supplementary. A lot of times complementary, you'll see a capital C with apostrophe because who wants to write complementary 7 or 8 times? Okay, so we can see a lot of relationships, and we can use relationships with angles to find missing angles. On this figure here, there's even more relationships. There's still the supplementary relationship. Angle 1 and angle 2 are supplementary, aren't they? And angle 1 and angle 4, as well as angle 2 and angle 3, they are pairs of vertical and therefore equal. So we still have those relationships, but because we now have a parallel line, we have the last thing that we mentioned. We have the corresponding angles. Corresponding angles, actually corresponding parts, doesn't have to be angles. Corresponding parts are equal if the figures are congruent. Corresponding parts are in proportion if the figures are similar. Corresponding angles are equal no matter whether it's similar or congruent. So corresponding angles are basically equal. So if I have two parallel lines cut by a transversal, I have still the supplementary relationships and the vertical angle relationships, but now I also have our last type, the corresponding. Corresponding angles are equal if the figure is either similar or congruent. And in this case, we have parallel lines. Okay, so they're going to be at the same slope, so they're going to form equal angles with the transversal. Remember, corresponding has the idea of being in the same location but on a different figure. So angle 2 is in the upper right-hand corner, so is angle 6. It's just on line L versus line K. So we have corresponding angles. Angle 2 and angle 6 are corresponding angles because they're in the same location but on different figures, right? You can see 1's going to correspond to 5, 3 corresponds to 7, 4 corresponds to 8. So corresponding angles are equal. Same location, but on the other figure. In this case, same location, but on the other line. Those are corresponding angles. And then, you remember this from junior high probably, and from high school, we can also have other equal angles. So let's just go ahead and say that let's say that angle 1 is 80 degrees. What is angle 2? Morgan?
100 degrees.
100. What is angle 3? Yes. It's also, why?
Because it's a vertical angle to 2.
It's vertical to 2 and?
Supplementary to 80.
Supplementary to 1. What is 4? It's 80. Same thing. We got all kinds of stuff here. Vertical to 1, supplementary to 2, supplementary to 3. What is angle 6? It's 100. Because it's corresponding to 2. 5 is 80. 3 reasons. Corresponds to 5, or 1. 5 corresponds to 1. 5 is supplementary to 6. And it's also supplementary to 7, which has to be 100. We can, given any one angle, we can find the other 7. Okay? With between vertical angles, supplementary angles, and corresponding angles. But if you took high school geometry, you also learned alternating or alternate interior angles, right? Remember? They're on alternate sides of the transversal, and they're interior to the two lines. Alternate interior. So 6 is 100 degrees because it is corresponding to 2, and it's alternate interior to 3. Okay? Same thing here. 4 and 5 are alternate interior. And then we have alternate exterior. But actually we don't even need these because we got so many relationships going on. You can see that 2 equals 7 because those are alternate exterior angles. So all kinds of relationships that you can do based on location and relationships. We can solve for missing angles. Okay, so if you look at 12.1, we are going to cover polygons next. But you need to read through 12.1. This is due tomorrow because of our class schedule. And you can see basically everything we've covered so far. We've got angles, lines, and geometric figures is in this section: complementary, supplementary, parallel. We are going to cover polygons more tomorrow. We're going to start with what a polygon is, and then we're going to also cover circles. But basically, you can see a lot of the information in here. It also then progresses to solid figures. Solid figures in 3 dimensions, and which figures correspond to which. So we're going to spend a lot of time tomorrow on the polygons. Then objective C involves angle problems with the, on page 522, you can see the alternate interior angles, the alternate exterior angles, and the corresponding angles that we're going to use. You can also see in the section C the vertical angles and the adjacent angles, a lot of the terminology we've gone through. We will go through the objective B in a lot more detail tomorrow with the polygons, which are plane figures, and circle, which is a plane figure. Then we will also go through the polyhedrons, which are 3-dimensional, and the sphere, another 3-dimensional object. Okay? And so that's the first thing that you need to do, is go through and read this and familiarize yourself with the terminology. Hopefully you're just reviewing the terminology that you learned in high school and actually had to use in high school. Okay, so we will pick up tomorrow with polygons.